Hello everyone and welcome to another Leetcode video. Today we're looking at count the number of good nodes, which was question 2 in weekly contest 410. So the question reads that we're given an undirected tree with n nodes and they're labeled from 0 to n-1. So you can see in this case we have 13 nodes labeled from 0 to 12 and the tree is rooted at 0. So we're also given a 2D integer array edges of length n-1, which says there's a connection between A and B, and this is essentially how we're creating this tree here. So you'll see 0, 1's an edge, we have a connection from 0 to 1. So what we want to do is find all the good nodes in this subtree, and in this case a good node is one where all of its subtrees have the same size, and size here means the number of nodes. So you'll see, for example, 1, this would be a good node because it has 3 subtrees, and each of these subtrees are of size 1 because they only have 1 node. However, 9 is not a good node because it has 2 subtrees, one with a size of 1 and one with a size of 2. So let's look a bit closer at this example and see exactly how we can solve this. So this is a slightly modified version of the example we looked at, and we're going to use recursion to solve this. Even though it's not the full tree, we can still get the idea from looking at this. And what we're going to do is use recursion and use what I like to call a bottom-up approach. Bottom-up. And what this means is that when we're at a node, we have to solve these subtree problems first, right? And you can think of this recursion as each node is its own sub-problem that we have to solve. And why is this bottom-up? Well, we have to know some information about its subtrees. For example, if we're looking at node 9, the question says we have to check if all of the subtrees are the same size, right? So we'd have to first go from 9, check all its subtrees, see what's the size of this, what's the size of this. So for this reason, we're actually going down as far as possible, solving these individual smaller problems, and then sending them back up to these nodes to figure out what to do. So how do we actually do this? How do we figure out which nodes are good? So let's say we're starting with this 1 node, and ignore the rest of this tree for now. Those will all work very similarly, but I just want to focus on a narrower problem to start with. So we're at 1, and we know we have to check all of the subtrees and see if they are the same size. So we start at 1. Now we know we have to solve the problem for each subtree. So let's go to 4. We see, okay, well, 4, this is a new problem, right, because we're doing recursion. So let's solve its subtrees. So it actually doesn't have any subtrees. So in this case, we're basically done. There's nothing else to do. So now what we can do is say 4 is done. This subproblem is done. There's nothing to do. So let's return the size of this up to 1, right? And we'll say, okay, one of your subtrees has a size of 1. And you'll see that the logic is the same for all these, right? We'll go to 3 and say there's no problem to solve here, and the current whole subtree here is 1, so we return 1 up here, and then again for 2, 1 up here. So basically what we've done is from 1, we've gone to all these different subproblems, basically solved them, and then return the size up. So now we're back at 1, and we say we have 3 subtrees, but these all have a size of 1, right? So what we're saying here essentially is that, okay, we've seen them all, they all have the same size, so we can tell that this is a good node, right? And again, we did this, we know this because we went to all of its subtrees, we got all of their sizes, and then when we got them all back up here, we compared them, so they all have a size of 1, and we know this is good. And now we've solved this problem for 1, right? What do we do at this point? Well, remember, we're going bottom up. So we have to take this result and we have to pass it back up to 0 to solve a bigger subproblem. So how do we do this? Well, we actually take all these subtrees, right? And let's say we have one of size 1 here. We have one of size 1 for 3. And we have one of size 1 for 2, right? And we know, we can see this, all these subtrees are of size 1. But now we're saying we've solved this problem for 1. So let's also add another 1 to represent this node. And what this represents, right, is this entire subtree. So now we're going to say to 0, your whole subtree over here has a size of 4, right? And this is how we're doing this bottom-up approach. We're going to solve these problems down here, And then 0 can say, this has been solved already. I don't care what's happening here, but I know that whatever the result is 4. Right? And then we can go down here and say, kind of do the same thing. So let's look at an example where we don't have a good node. So let's look at 9. So when we come down here, we say, okay, my subtree size is 1 here, but here is actually 2, right? And it's 2 because we have 2 nodes in the subtree. We have 10 and we have 11. So we can see here that 9 is not a good node, right? So this is kind of how we're going to do it. We're going to, for each node, go to all its subtrees. We're going to return the counts up, and then we can use something like a set to find the unique ones. And if there's only one unique value that we have, then we know it's good. Otherwise, it's false. And we can do all of this in O of n time. And there are really 2 steps to doing this. So the first step is that we're going to take all those edges, the edges that we're given, and make them into a graph, right? We're going to convert this into a graph. That just makes it easier for us to traverse through this tree, right? And then what we're doing is we're going to start at 0, and we're going to do this process that we just talked about. We're going to go down to all of our children. We're going to solve those subproblems, return those results back up, and then we're going to solve the problems all the way up until 0. And you'll see exactly how that works in the code. So the first thing that we're going to do is take these edges and create a graph from them. So we're going to have this graph in our default dict, and then for each edge, we're just going to say, this is undirected, so S is going to point to D, and D is going to point to S. Then we have this instance variable that we're going to use to just keep track of the number of good nodes. And then this find nodes function is where we actually do most of the work for this question. So for each recursive call, what we're going to do is say, our current size is going to be 1. And what this 1 represents is just the current node that we're on. So we're going to say, this subtree right now, we have the node that we're looking at, so we know it's at least size 1, but then we're going to go and get all of its subtrees and get the total amount that lives in this tree. So what we're going to do is say for neighbor, for all the neighbors that I have in the graph, and here's a special case. We're going to say if our neighbor is the same as the previous, and what previous is in this case is just the node that we just came from. So say in our example, we're rooted at 0, and then we're going to go to 2, right? But now when we go through 2's neighbors, 0 technically is a neighbor of 2, but we just came from there, right? So this is the way that we avoid doing repeated work. So when we see that the neighbor is the same as the one we just came from, we just skip over it. Then what we do is we're going to find the size of all of our subtrees. And we do this by taking that neighbor. We're going to pass in that value to our recursive function, and we're also going to pass in our current node as our previous. And this is just so that in the recursive calls for our children, we don't go back up to this node and do unnecessary work. So we're going to take that size, and we're going to add it to our size variable. And this is saying we found the size of this subtree, so let's add it to the total size of the current subtree that we're looking at. And then we have a set here of our child sizes, and this set represents the size of all the subtrees of this current node. So we're just going to basically add that into our set. So then here's where we check if it's a good node. So we're saying if there is at most one unique size in that set, we know it's a good node. And what does this mean? So if there are 0 nodes, this is the case where, or 0 values in this set, this means that there are really no neighbors that we went through, right? And this is kind of the case where we have a leaf node in our tree. Technically, there's no neighbors to go through, but it's a good node, right? Because all of its non-existent subtrees are of size 0. So that's one case where the size would be 0. The other case is where it would be 1, right? And if it's 1, we don't know how many subtrees there are. There could be 2, there could be 10, there could be 20 subtrees, but we know that if we only see one value in our set, then they all have the same size. And if we have, say, more than one value, say we have 2 and 7 in our set, we know that, well, those are subtrees that have different values. So this cannot be a good node. So only if the length of our child sizes is less than or equal to 1, we want to increment that good node value. And then finally, at the end, we return our size. And what this is doing is saying we're taking the size of all the subtrees for this node plus the current node, and we're going to pass it back up to our parent node and say, we've solved this problem for you. Here is the size of me and all my children for that node to then use. So finally, we call this function rooted at 0, and we have none as our previous value to start with. Then once we do all that work, we just return our self.goodNodes value. So let's submit that and make sure that it works. And it does work. So hopefully this made sense and was helpful, and thank you for watching.